आतापासून कॅमेरा चालू
चालू केला.
चालू होता.
Hello.
Hello.
Yeah, are we getting started now?
Maybe they're waiting for so.
Hi, Professor. Shall we start? We're already 10 minutes into the call.
Yeah, I think we can start. I mean, both Dinakaran and I are here.
Okay. We spoke about the standard transpiler versus oral transpiler, right? Can you throw some light on it?
Okay, so maybe that's something I can take.
Yeah.
Uh, so, just to recap, Transpiler is a module that takes in high-level user-written program, a quantum program, to efficient intermediate representation. Okay. Uh, and intermediate representation, like some you can think of some analogous to an assembly language for quantum computers. They also try to make it sort of hardware, technology agnostic, and so on. So anyway, so that's a transpiler, right? A standard transpiler in Qiskit, we try to, like, okay, one point I would say. So this is, let's say, this is a step that runs on classical computers to optimize the instructions to be run on quantum programs. So at the end of the day, it's a classical tool that is a precursor to running a quantum program on a quantum hardware, right? So the standard transpiler routine in Qiskit, we try to be uh, okay. I mean, standard enough to use that word again, to make it run on any classical or like almost on most classical hardware platforms. We have a wide variety of operating systems. We have a wide variety of instruction set architectures, like so many things, right? So, I mean, the future that we are working towards is to make it as standard as possible. So, uh, from that perspective, it makes it slightly challenging to incorporate ML routines as part of the standard transpiler routine as of now. So we have mostly tried to have algorithmic based optimizations that can all be compiled and then sort of gotten together as a single solution of uh, the transpile the Qiskit SDK, let's say, right? So at the end of the day, what it takes to go from, the lecture we covered different stages of transpilation, right? We have mapping, routing, sort of circuit synthesis, unitary synthesis, and so on, and then sort of gate optimizations and scheduling. So many of these, you can, I guess, like many of you would be uh, aware of different algorithms. So, of course, there is an ML way of looking at this, but there is also a standard algorithmic based approaches uh, that can be used for it. So, the SDK, we focus on algorithmic based approaches so that it's easy to install it on different compiler platforms. So, that's the standard routine. Of course, we also make it extensible so you can have any circuit optimization that you can have as a quote unquote pass, and that pass can also be an RL based pass if that's what you want to like add as a plugin. Does that answer the question?
Yeah, yeah. Thanks, Professor. Just to follow up, right? So when we run the circuits in Qiskit, it still runs on the transpiler behind, right? So that runs on a classical computer, right? Because it's just a simulation. Um,
No. Okay. So not exactly. So like I said, there are maybe four steps of. You can. There is one possible abstraction of looking at an end-to-end quantum program execution.
mhm.
uh, you can think of it like four high-level steps. The first step is to map the classical data into quantum circuit or quantum state, depending
Okay.
on whether or not the input data is. The second step is to optimize this particular quantum circuit that we have mapped. Okay, and that is bulk of the transpilation comes in there. The third step is the actual execution on the quantum hardware. Okay,
I
and that
see.
is the core quantum part of things. So after you come up with an optimized circuit, you run this optimized sort of set of instructions on the quantum hardware. And then the fourth step is some post processing or some iteration that you want to do. So steps one, two, and four are run on classical computers to either sort of prepare an optimized set of instructions or to do some post processing. The third step is the actual usage of quantum hardware, where you run these optimized set of instructions on the hardware. So it's all transpilers to one of the main preparatory stages to run it on a quantum hardware.
Got it. Okay. So basically, it will optimize my circuit that I prepared and into a state where it can run in hardware.
Correct. There is, yes, it does, let's say, 90% of the optimizations. There is also something, like I said, the particular transpiler will try to make it hardware agnostic. So the output of this assembly, the output like an assembly form that is taken into one more layer of optimization and scheduling, which is hardware specific. IBM will have its own way of doing it. Other companies will have their own way of doing that. That is also happening. That takes the output of a transpiler and then sort of does some hardware specific optimization and scheduling, and then it runs.
Okay, got it. So there are other optimization, other transpilers also available from different um, companies. It like IBM has a transpiler. Similarly, a respective like public has a different transpiler or this.
I think others try to have something on their own, uh, but I think nothing at the scale or like as popular as Qiskit as far as we know.
Okay.
I mean, you can, let's say there is this forum called, the name is skipping my mind. What is that, Ritajit? The open organization in the US that runs survey every year of all quantum tools. Uh,
Yeah, that's something
Anyway, I'll
unitary
find.
unitary
Ah, correct. Unitary one
part.
or the
Yeah, yeah.
right. So they run this survey every year of different quantum tools used for different steps.
Mm-hmm.
Unitary Foundation. I think they've renamed themselves Unitary Foundation. So Yes, so they conduct a survey of different tools available for different steps of quantum program execution. I think that's probably one place you can look at for different tools.
Okay, sure. Yes. Just one follow-up question. So this transpiler does not optimize the noise the circuit I prepare, is it? It's just
Uh, okay, there is a provision for that also. One of the steps of transpiler is to include the hardware specific configuration. Okay, so let's say like the six stages, if you remember from the lecture,
yeah.
mapping and routing, and some of these steps, there is also a provision to optimize with respect to the hardware. And also there is a possibility of adding the basis gates of the hardware that the particular hardware supports, because there are many different universal gate set possible, right? So and in fact each superconducting will have its own basis gate set. Other technologies have go place set. Even in superconducting, as hardware evolves, we realize that different gates are like easier to implement and more optimized to implement and so on. So yes, basis transpiler also converts sort of arbitrary gates and operations the user writes to uh, basis gates that's supported by the hardware.
I see. Yeah. Thanks, Professor.
Professor, when you talk about the gate error codes, error possibilities, whatever we are getting from the hardware part, so is it fixed and known only when the qubits are prepared and that, or it will be updating over time? So the
Oh,
error.
it significantly updates. I mean, like evolves over time.
Okay.
Uh, yeah, so it's up to us to provide the latest noise configuration in any manner. So yeah, so how we do it is, if you're connecting to the IBM Quantum service, so depending on the, if you're running it in the simulator, let's say some custom simulator with a noise model involved, there is uh, a periodically updated noise profile that you can potentially import. If you're connecting to the actual hardware, anyway, you only specify the name of the hardware. And then in the backend, we have a service that can pull up the latest. We also periodically run, uh, let's say, characterization of our hardware, different routines to characterize noise profile and other things about the hardware, and sort of included as part of the compilation routine. That is periodically done. Sometimes some of our users would want to run that at the beginning of their execution itself, uh, some of the characterization routine. So there is also provision to do that.
Thank you, sir. And Professor, can you please give us some detailed explanation of this circuit cut mechanism, wire cut, and the separating of gates, right? Can you just give us some detailed explanation of it about the wire cut part?
Okay, maybe Ritajit, you want to take it because you have been doing the latest research.
Yeah, yeah, yeah. Sure. So just give me a second.
Yeah, just basics of all gate cutting and wire cutting, and then knitting also. If you can please highlight all those things, it will be good.
Okay. Yeah. So, okay. Cutting and knitting are essentially the same. I mean, different orgs call it with different names, but they are kind of the same thing. Mm. Is my screen visible?
Yes, yes.
Yes.
Okay. Yeah. So the main idea here, the way it started basically is that if you take, say, you have a classical computer. Let's, since you asked for an overview, I'm just giving you an overview here. That let's say you have a classical logic like this logic function. So it requires 4 bits, but you have, say, only 2 bits in your classical computer. So how would you run this 4-bit circuit on a 2-bit machine? The easy way will be that you will take this part separately, you will calculate AB and store it somewhere. Then you will take this part, you would calculate B bar C and store it somewhere. And again, you will do this part, initialize with AB and B bar C, and you calculate this. So instead of a single circuit execution, you now need 3 circuit executions, but you are able to actually do a 4-bit computation on a 2-bit device. This is all classical. Now, what changes is when you go to a quantum circuit. Let's say I have tried to keep a very similar kind of notion here. So I now have a 2-qubit quantum circuit on which I want to run this 2-qubit quantum computer on which I want to run this 4-qubit quantum circuit. So if I play the game as before, I am starting with this part. I will calculate this. Now the problem is, previously I said that you need to store AB somewhere, and classically that's very easy to do. But quantum mechanically, this output is usually a density matrix. So you cannot really store a density matrix, and even then today we don't have a QRAM. Whether we will have it, when we will have it, we don't know. So this storing itself is a problem. Second, let's say second the for the same second part of this circuit, the same problem. Now let's say even if you are able to store it, let's say someday we have QRAMs and something, you are able to store this in QRAM. Now the question is that how will you initialize? So if you remember, the third part was we are initializing with AB and B bar C, the last gate. So how do you initialize on a density matrix? Because density matrix is a classical distribution of multiple quantum states. You cannot prepare a distribution as an input to a quantum circuit. So this leads to an immediate challenge that if you want to run a bigger circuit on a smaller device, it is very easy to do classically. It seems impossible to do quantum mechanically. So what is done ideally is that you want to do a, let's take gate cutting first. So you want to do gate cutting. What it does is, ideally what I would be happy, you have a 2-qubit gate. So why is a 2-qubit gate problematic? Because when I write A and B on the coupling map, A and B may not be sitting next to each other, they may be sitting far from each other. So just to implement this 2-qubit gate, you may need many swap gates. So here if you see an example, let's say this is a quantum hardware, this is the old 27 qubit devices, and you have a quantum circuit like this. If you look into this part of the gate, here every I is connected to I plus 1. So you can easily have a straight line like this and it works. But look into this one. So this gate needs to be connected, this qubit needs to be connected to this qubit via a 2-qubit gate. And there is no way I can do that directly. So the moment I go and transpile, it will add multiple swap gates, and you can see how it goes. The depth of the original circuit is 13, the original circuit like this, but the moment you transpile, it goes up to 52. So that's a huge increase. So it will be really good if I could replace this 2-qubit gate with single qubit gates. But in general, you can show mathematically that there are 2-qubit gates where just replacing it with a single qubit gate is not possible. What is possible is if you do this multiple iterations of this. What sort? Something like this. Say I have this RZZ theta gate. You can write it as a combination of these cases. So this is identity, this is applying Z gate on both the qubits, this is measuring the first qubit, applying an S gate on the second qubit, measuring, applying S dagger, and so on, all of those. And this you have to do, so there are 6 circuits that you have to run now, and each circuit is running with this probability. Now note one thing, irrespective of the value of theta, so this and this cancels, this and this cancels, sine square theta plus cos square theta adds up to 1. So this looks like a probability distribution from which I can sample. But note that depending on the value of theta, some of these can be negative. So what we say is that this is a quasi probability distribution. So this is the idea of gate cutting, that you take a circuit, you cut it down like this. So you are replacing a 2 qubit gate using single qubit gate, but not a single instance of it. You need to now run all these 6 instances. So instead of a single gate, you need to run 6 gates, and that gives you an effect of circuit cutting, an effect of this 2 qubit gate. So that this is what we call as circuit cutting, basically. And if you want to think of wire cutting in particular, here the idea is, say you have a circuit like this where U is a gate, V is a gate. Now I can put in an identity anywhere I want, right? Identity is not doing anything. So let's say I am putting in an identity here. So identity can be written down like this. So you can say identity is 00 plus 1 1. You can show that identity is plus 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 minus minus. So you take any basis, identity will just be the summation of all those terms in the basis, like 00 plus 1 1 plus 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 minus minus. You take any basis that you want. So just showing this as B. The original circuit, now I can write it down like this. So I am explicitly stating the number of qubits and the gate which acts on which qubit. So U is acting on qubit 1 and 2, V is acting on qubit 2 and 3. Now the idea is here, if I put in this identity between U and V, then I can just write it like this, right? I have just put in the identity. Now, you see this is acting on qubit 2. Now let's separate out the two things. Mathematically, you can separate this part out and you can separate this part out. What does this, so this is a 2 qubit circuit because it's basically acting on 2 qubits. This is also a 2 qubit circuit. This is acting on 2 qubits. Physically, what it means? Physically, this means that you are measuring in basis B and you are preparing in the eigenstate of basis B. So if you measure in, say, Z basis, you are preparing in the eigenstate of Z basis, that means 0, 1. If you measure in X basis, you are preparing in the eigenstate of X basis, that is plus minus. So here you measure in a particular basis, here you prepare the qubit in the eigenstate of that basis. And this is a more generalized scenario. It looks a bit complicated, but the main idea is that you are simple like this. See, you are measuring in basis O and you are preparing in the corresponding eigenstate of O. And since any density matrix can be written, so when I'm cutting this, this is in general a density matrix, right? This is what we argued in the beginning, that this is a density matrix. So a density matrix can always be written down as a linear combination of the Pauli gates, because the Pauli gates span the 2 qubit vector space, right? So I can write it down as a linear combination of the Pauli gates, I, X, Y, Z. What does this trace of AI means? This is the coefficient of I. This is the coefficient of X because it's a linear combination. So I have a coefficient. How will I get this coefficient? I will get the coefficient by measuring in that basis and that probability of measurement, the probability of outcome. That gives me the coefficient. And how can I prepare in I? It doesn't mean anything to prepare in I. Prepare the qubit in I. What it means is you prepare in the eigenstate of I. So the main goal is that you measure in a particular basis. That probability of outcome gives you the coefficient, this trace of AOI. This gives you the coefficient when you measure in basis OI, and then you prepare the following qubit, this cut qubit, in the eigenstate of that basis, rho I. This is the overall idea of this. So if you see, this is the idea that when you measure in basis I, you prepare in eigenstate 0 and 1. Both of I, 0 and 1 are the eigenstates of I. 0 and 1 are also the eigenstates of Z. So when you measure in basis Z, you want to do this, then X this, and Y this. So This is how you can actually do wire cutting here. But if you see, if you want to notice, I mean, yeah, these two ideas are very similar. You can say as if, so when I am drawing a picture like this, you measure here, you prepare here. This measure and prepare, you can call it together as if it's a virtual gate. So the idea is that you always cut gates, either a real gate like RZZ, where I showed you how to cut an RZZ gate, and you can have many gates like this. So, okay, not this one. So as I was showing you that with RZZ gate, today we have C0 gates and CZ gates, and with RZZ gate, by fixing the angle properly, you can create those gates. So if you know how to cut RZZ gates, you know how to cut C0 gate, you know how to cut CZ gate. And similarly, if you want to cut wires, you can think of this gate is getting cut in this way. You are preparing the first qubit in the measurement basis and the following qubit in the corresponding eigenstate. So yeah, so this is how the cutting goes essentially. And when we say knitting, what it means, again, cutting and knitting are the same thing. Finally, you need to do a sum over this ci phi I. What is ci? Ci is basically when you are, if you look into this, identity is 0 0 plus 1 1, z is 0 0 minus 1 1. So this plus minus these coefficients are the ci's. So individually you get the outcome of each of these cases, and then you either add or subtract accordingly. And what this gives you is the expectation value of a particular observable. If you want the final state, no, you cannot get the final state using this. You will get a probability distribution, but that's basically a classical distribution from which you can just go and calculate expectation value. If you want to say that after doing circuit cutting, I will not measure, I will use this quantum state as an input to say my algorithm, that is not going to work, because there are some information loss here which allows you to calculate expectation value but doesn't allow you to mm, take this as a quantum state which goes as the input to an algorithm or something that you are developing. Yeah, I hope that helps.
Professor, you mapped the virtual qubits versus the physical qubits, right? And then you formed an I-shaped pattern of the physical qubits. Is there any specific reason to choose that structure?
Is this from circuit cutting? I'm guessing not.
No, 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 not related to circuit cutting. It's about the mapping qubit selection using Mapomatic.
Okay, so maybe I can also take the
Yeah, you can
Mapomatic.
take that. Yeah.
Mm, so the idea in Mapomatic is, if you see, ideally what we want to do, we want, let me again share my screen and show you this. Can you confirm if this figure is visible?
Yes.
Okay, great. So the main idea of Mapomatic here is that, we have a few things, like you or somewhere else were asking, Lina Karan, that whether transpilation can take care of the noise as well. It can.
Correct.
So the point is that already mapping a circuit, even if there is, say, there is no noise on the hardware, even then doing an optimal mapping of the circuit to the hardware so that the number of swap gates is minimized, this is an NP hard problem. So that means you already have to go to heuristics. Now, when you are putting in noise in the system and you put in one more extra constraint, that you have to minimize the number of swap gates and you have to select a layout which has the minimal noise. When you add this second constraint, it becomes an even harder problem, a problem which was already NP hard. You are making that even more complicated. So there are already papers who try to do this kind of joint optimization, but you can understand how difficult that will be. So the approach that Mapomatic takes is, it says that first forget there is noise in the system. Let's assume there is no noise in the system. Now you just do whatever best you can, use your best heuristics and everything to map this circuit to the hardware so that the number of swap gates is minimized. Let's say that this is the mapping that is used. So say maybe qubit 0 is this, 1 is this, and so on. So this is kind of the mapping that is used on the hardware. Now what it is saying is, now let's come back and say that no, there is actually noise in the system. I cannot just ignore that. So what can I do? I have used this mapping. If I use a mapping here, they are isomorphic. That means the ordering of the qubits that I have used in this particular layout versus if I have used this particular layout, the ordering of the qubits doesn't change. If the ordering of the qubit doesn't change, then the number of swap gates required here versus the number of swap gates required here will be the same. So
Correct.
what you can do is you can start finding out different isomorphic layouts. Like this is an isomorphic layout. This one in behind is an isomorphic layout. You can have many such isomorphic layouts. So once you get the isomorphic layouts, you know that the number of swap gates are not differing in these layouts. So now what you do, you look into the calibration data of the quantum computers. Like you go here and you say this is IBM Boston, so you have the calibration data of each and every qubit. You go and find out what is the noise profile of this layout. So that's just a function of calibration data. That's all. I mean, this single qubit gate has some error, this two qubit gate has some error, measurement has some error. So it's a function of all of those. That gives you a real number, the layout score or noise profile, however you call it. So when you calculate all of the noise profile of all of these isomorphic layouts, just select the one which has the minimum noise profile. So this is the idea of Mapomatic. Divide the complicated problem in two parts. First, map to minimize the number of swap gates. Next, find all isomorphic layouts because that is going to retain the same number of swap gates. Find out the noise profile of each of these isomorphic layouts. Whichever is the minimum, place your circuit eventually on that layout. So if it turns out that the noise profile of this layout is lower than this, I will finally select this layout for my final mapping.
I see. Okay. Comparing to these two layouts, whichever is having less swap gates, I prefer to choose.
Not list swap gates because these two are isomorphic layouts. So the number of swap gates will be the same, but the error rate of the qubits is not the same in each of the. I mean, the error rate of the qubits differ, right? They are not uniform throughout the hardware.
I see.
Therefore, the noise of this layout and this layout is in general not the same. So you will choose that layout which has the lower noise profile.
Okay. Got it. So placing the qubits in the hardware is one of the key criteria to reduce the noise, right?
Yes, yes, of course.
So we learn by building the circuits and fitting it into the physical qubits, right? Like
Hmm,
how do
hmm.
we, I mean, we understand theoretically, but if we have to implement it in a Qiskit, right?
It is already implemented in the Qiskit transpiler. That's what the transpiler does, right? It's I mean, it's not the only thing that the transpiler does, but that's one of the things that the transpiler does, trying to find a good mapping that minimizes the number of swap gates. So that's the layout and the routing pass of the transpiler. It uses what is called the Saber algorithm.
Oh, I see. Okay, it means optimizes the circuit and makes it less noise.
Hmm,
Uh, okay.
hmm.
So it internally maps this virtual to the physical qubit, is it? The transpiler does it, or
Yeah, the transpiler does it.
okay, I see. Okay, thanks.
So less noise could come from multiple different ways. One is, like Ritajit would have explained, mathematics, like how, let's say, different gates are better off to be run on different qubits, something like that. Uh, and implicitly, even gate optimization leads to less noise, right? And that is also leads to more efficiency, but it also leads to less noise because less gates means there is less noise in the circuit. So, uh, so sort of gate optimizations help in both ways. And both these, all these things transpile. Yeah.
Yeah, thanks, Professor.
Hello. Hello.
Yeah, right. Yeah.
Uh, Sir, this transpilation is a generic term or it is related to only IBM quantum computers?
It's a generic term that the traditional computer science compiler community also used it for, let's say, certain type of compilation. I think transpiler means transform plus compiler, something like that. I mean, that term existed even before. We thought for this particular thing, what we do, which is convert high-level user program to assembly, we decided that is used. But even inside IBM, we use it interchangeably, transpilation and compilation. But as far as I remember, it's not even specific to, I mean, it's not specific to IBM, not specific to quantum computing also.
Okay. And it then strictly depends on the quantum computer architecture and different types of qubits.
Uh, no, so there are many things which are agnostic to hardware. Different gate optimizations are agnostic to hardware, but there are also hardware specific optimizations for it. So it's like what we have seen in the classical compiler. We'll have hardware specific aspects, we'll have hardware agnostic aspects. Yeah.
Okay. So if we want to like study more detail or go into detail, what is the broad topic name we have to search for?
Uh, Quantum compilation, maybe.
Quantum compilation. Okay.
Compilation of quantum circuits.
Yeah. Thank you, sir.
Professor, can you suggest any book or anything on these topics?
There is not a book yet. Uh, Let me think if there are any research papers around it. Uh, but one place certainly to look at is, in Qiskit, even though the preset fast manager, the default execution pipeline has a specific thing, we have about 100, 150 individual passes, like the circuit operations that are implemented. So I think that already will give you like the entire breadth of what exists. Let me also think to see if there is any sort of survey paper that has been put in, but nothing comes to top of my mind. Rituji, do you want to take the Saber question? Layout?
Okay. So I don't have a slide or anything that I can show you on Saber, but the main idea is something like that. You know, you start with some random selection of qubits, and once you have selected a random layout, so that's a random selection of qubits. Say you say Q0 goes to Q5, Q1 goes to Q7. Some randomly you select something, then you start putting the gates one after another, and wherever required you start putting swap gates. So when you put swap gates, I mean, if you look into the Saber paper, the way it goes is that it looks into the circuit and it logically partitions the circuit. So the first layer of gates which are not yet placed, say you have a circuit with Hadamard and CNOT, just an example, a 2 qubit circuit, Hadamard and CNOT. So the first layer of gate is header mart. That's how we can divide. The first layer is header mart. So from that first layer, you start putting in gates wherever feasible. Like header mart is a single qubit gate. You don't need any swap gates or anything for that. You just put in that header mart gate. But say now after header mart, you also have a CNOT, like I'm saying. And this CNOT two qubits are not neighbor in each other. So what you want to do is to make a decision. First, you may put a swap gate here and make sure that you can apply that CNOT. Say the Q0 and Q1 here, Q0 is mapped to 5, Q1 is mapped to 7. So 5 and 7 are not neighbor of each other. You want to put a swap gate. Or you can look ahead to the circuit, and by looking ahead on the circuit you can try to see if you put a swap gate here, how many other swap gates you can require in the later part. Just because you flipped 5 and 7, does it imply that a lot of other gates in the later part of the circuit is disturbed? If that happens, then you don't put a swap gate. So you make a decision that okay, this is not a great position to put a swap gate, because if I put a swap gate here, then I will require many other swap gates in the later part of the circuit. Or if you find that is not happening, you put a swap gate here. So this is how you start making decisions, and you actually route the circuit. You put in gates as required, and you find a final solution. Now note that since you are putting some swap gates, the ordering of the qubits gets disturbed, right? You start from say 5, q0 is placed on 5, q1 is placed on 7, but just because you put a swap gate, maybe you end up at 7 and 5, the opposite way. Now you start the same idea from the back of the circuit. You look the circuit in the reverse way. You start with 7 5, and you start doing the same algorithm trying to find an ideal mapping. So this is how you kind of keep going back and forth again and again till you find the minimum number of swaps. You do this again and again for a predefined number of times, and this you keep on doing, and you return the best layout that you are finding where the number of swap gates is minimized. So this is the overall bird's eye view idea of how Sabre works. Again, it's a heuristic, so of course, I mean, there is no guarantee that doing it like this is going to be really great. And you can understand that a lot depends on how do you select that initial layout from where you start. And there have been studies which shows that if you can in some way, there is no, to the best of my knowledge, there is no algorithmic way yet to do that, but if you can provide a very good initial layout, Sabre gives you almost the perfect result. If you can't do that, then it's a heuristic like this, and it is just trying to do as best as it can. Yeah, I hope that answers.
Good morning, sir.
Hey, yeah,
Yeah,
good morning.
Sir, my question is regarding where to use transponder in local machine or in any other server type. Why? Because while I am working on the machine learning, I want to the machine learning, deep learning is that one regarding machine learning for the purpose of image processing. If we want to build a circuit for that image processing in the quantum, it will take a large amount of circuit. So, in order to process in that circuit in our local machine, is there any possibility to run it in any platform?
Right. I think that sort of. I think there is a provision for both, depending on what you have. Maybe we'll find after the runtime service still exists, right, Ritujit? That lets compilation on the server side.
no, 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 it
It's
doesn't.
it's not there.
No, it
Recently, it
does
stopped.
some lightweight
Okay.
compilation in the server side that you can opt for or you may want to skip, but you have to do the transpilation at your end at this point.
Yeah, I think that sort of keeps evolving. Maybe
Mhm.
next year, I think there is a possibility that we'll be able to do it server side. But yeah, as of today, yes, you can just only do it on your own machine, and then the circuit is sent to the server to run.
Okay. So I'll just add on to that when Dinakaran was saying about server side. So there are some transpilation services that you can use. So in particular for AI thing that you have this transpiler service. If you use the transpiler service, it runs in the cloud and it returns the data to you. But this is not in runtime. I mean, this you again have to do before you send your circuit for execution via runtime.
Okay, thank you, sir. Thank you.
And that is independent of the application that you want to run. Like this particular flow is common for any app.
Hello, this is
Go ahead, please.
Bhaskar. Okay. Dr. Dinakaran and Dr. Ritajit, thank you so much for taking this additional class. So, first of all, I have a couple of questions. This may look like a very basic one, but I always have one doubt. Is when we compare classical computers to, because we are talking about all the hardware and how to interact with hardware. So, how are we really doing an I/O to these quantum processors? So when we talk about classical computers, we have different ways of doing I/O. We have TCP/IP, all these keyboard, mouse, all those things will be there. But how are we really inputting data or initializing everything at a quantum processor level?
So let me start with what I know, and then the Pradeep can take over. I mean, first of all, we are both at sort of computer science side of things, and we have relatively less knowledge about the sort of electronics and physical aspects. But from what we know, we talked about compilation and so on, and then like these compile the execution program is sent to the so-called control electronics, and for the superconducting qubit hardware, there is some form of electromagnetic pulses that these control electronics send to qubits, and then they receive back. So that's sort of one line summary of uh, what I know. And qubits are mostly static, so it's morely these control electronics that interact with these qubits to either store information or retrieve information or do some gate operations.
Okay, thank you. Yeah, yep, got it. But what we are doing in the Qiskit or using Python or whatever we are doing in the cloud, we are just submitting a program. So, where are we submitting that program? To where means which what part of this
Right,
quantum computer is
got it.
getting processing that one?
So you're not directly submitting to a quantum computer. You're submitting to some classical control that sits near. I mean, eventually, if it passes through cloud, it eventually reaches a classical control for a quantum hardware, and then that
Oh,
classical control is what interacts with the real quantum part of the device. And the
oh,
lowest
I
level of the
see.
classical control is what we call as control vector, which are
Oh,
usually
got
some
it. So there
pre-programmed
is a.
instructions on FPGAs that interact with the quantum processor.
Oh, got it, got it. So there is a special type of controller is placed in front of this quantum computer, so which can understand
That's
the
right.
electromagnetic pulses or something like that into quantum chips, right?
That's right. Yeah.
Oh, thank you so much. That's what I was having doubt. So one other thing, do you know if we have a hybrid computers like now you mentioned that there is a classical controller, but do we really have like a hybrid mechanism, like a classical chip and a quantum chip together on a board, much like a CPU and GPU? Do we have something like that? So we have some calculations we do in QML and all, where we do a quantum kernel or some, we can do that one. So we do certain things in classical, transfer to quantum, get it back, process. All these things are happening. So for this reason, do we have anything like a hybrid model where classical and quantum chips are on the same circuit board or something like that?
So I take your question in two parts. One is the the possibility of hybrid quantum classical computation. The second is co-location of a classical processor on along with the quantum chip. So
Yes.
as of today, for the second part of the question, I don't think there is a co-located. I mean, there is co-located classical quantum chip, but that's only used for control electronics at this point. We don't have,
Oh,
let's say, a
control alert.
massive.
Okay.
Yeah, we don't have massive, let's say, co-located classical and quantum for computation uh, in terms of hardware
Okay.
co-location. But having said that, we really think the future of quantum computing is when it's used as part of, like traditional workflows, where quantum is also yet another computing resource that's used. Okay, like quantum is not going to be uh, like useful for end-to-end workflows. There will be some specialized, complex niche computations for which quantum computer will be significantly better, and they'll be used as part of traditional workflows. That's why like we have this so-called paradigm of quantum-centric supercomputing, where a traditional HPC or a supercomputing architecture that has composition of CPU, GPUs, and maybe some AI specialized hardware that is used as part of workflows, and then all these tools are extended to have quantum identified as one other computing resource that they should use. But this co-location happens at a higher level layer, and there is workflow orchestration and sort of resource allocation involved in those kind of things, but not in terms of a hardware co-location yet.
Oh, okay. Thank you. So, yeah, I have one more question in this one. Like, when we are talking about the basis gates, right? Basis gates, how, where do we find the what basis gates are being are there in a type of processor? Like, say, for example, Henron or Eagle processor. So where do we find some literature or anything on this basis gates?
So, at least from IBM, for each of the hardware we provide, it's publicly listed in our this strategic link on phone. So, like if you search for IBM Quantum platform, right? Like the same place where you have learning resources and so on. Yeah, thanks. So for each of the
Oh,
hardware, we list, the entire sort of configuration as of today, and also the basis gates. Many things you can also programmatically obtain this, but
oh,
this is
okay,
the way you
okay,
can
got
look
it.
at.
So yeah, now I know where to find it. Okay, thank you. So basis gates. Okay.
Right. And similar, this is the same place where you can find, like we earlier talked about characterization of hardware, the hardware, what's the noise, and different aspects, right? So the latest thing and about when the hardware characterization was done, it's also there on the same page.
Okay, thank you. So one other question, Ritajit, Dr. Ritajit, sorry. Last week we asked about, I asked about the notebooks. Will you be able to get those notebooks? Actually, we need to run some programs for even for assignment or for us to test it, whatever you have taught, but we don't have the notebooks.
This is on error mitigation or on circuit cutting?
Uh, we don't have anything. Nothing is there from module 8.
Okay.
In module 7 also, there were some of them, but they were not there at all.
Okay, I'll ask the NPTEL team, but just to get you started immediately, what you can do is let me share this two links with you. There are already existing tutorials. I mean, you should get the tutorial notebooks that is done for the NPTEL. Of course, I'll talk with the NPTEL team, but let me try to find this.
Okay. So
Yeah.
are you sharing
So
those links?
yeah, I'm just sharing those links in chat. So if you look into this notebook, this is on gate cutting, and the second link that I am providing, this is on wire cutting. Just note one thing, that these notebooks, of course, show a lot of things um, on how you can use the circuit cutting very efficiently. So at so just to get started with, if it feels a bit like overwhelming, you can also look into these tutorials. There are 4 tutorials here, which are way simpler, I would say. I mean, if these first 2 tutorials immediately seem a bit overwhelming, I would request that you start with this third link. There are 4 tutorials in the third link, and with very simple gates, it shows how you can cut a gate, how you can cut a wire, how you can use this automatic cut finder to do it for you, do both gate and wire cutting for you. You don't have to do anything. All of these things are applied in the first 2 tutorials that I sent you.
Okay, thank you, Dr. Saji.
And actually, there is one more thing I want to say about these tutorials, right? I mean, not just these specific tutorials in general. You know, if you go to the Urban Quantum Learning platform, there'll be a large set of tutorials, right? The name sounds a bit simplistic, but you know, it has everything from the most basic to any interesting technique useful for users of quantum computers, even the most advanced ones that came up in the recent years. There is a team of PhDs that keep an eye out for interesting tools and techniques that come up in the research papers, either from IBM or anyone who uses real hardware. And then, if a technique or algorithm is found useful and repeatable, they spend a significant time converting the theory into the most efficient and the scalable way of implementing it and create a tutorial out of it. So, yeah, this is something we provide even to our most premium sort of partners and organizations who work with us, and everything is available on the learning platform, which is a great learning
Okay.
resource.
Okay.
Sir,
Thank you.
shall you share that link, sir, please?
Yeah,
Which one? I shared the links on chat, if you see.
Yes, it is regarding Quizzkit itself. And
Sorry, what link you want? I mean, I shared the circuit cutting notebook link.
yes,
right. If you go a level up there, I think in that same page, I think probably we'll see all the tutorials.
Let me just
And
share
then,
once more and I can show you.
okay, okay. Thank you.
So if you just go to this, say here itself, if you just go to quantum.cloud.ibm.com, you will
Okay,
end up something like this. If you are logged in, logged out, doesn't matter.
yes,
Just
sir.
come here, and here you will go see tutorials. Okay, so this is the list of all tutorials. You can see there are sampling algorithms like chemistry, QAOA. I think these are the things you have already learned.
Yes, sir.
These are like VQE, kernel training, QSVM, all of these stuffs. Then fault tolerant algorithm are just coming about, but how you better use all of those things, like this transpiler, AI powered transpiler, how you can better use Saber, this is also here. um, then you have functions is slightly different, not going into that. Then you have add-ons, and within add-ons you find this cutting cut I mean, yeah, these three um, things here: wire cutting, and this is for periodic boundary condition, and this is for general gate cutting. Then you have error mitigation tutorials, and more recently error detection tutorials as well. So all of these you can just go and find here.
Sir, small doubt, sir. Small doubt,
Yeah.
sir. Yeah, this wire cutting and gate cutting is there now.
Mm.
So, is it comes under optimization that can be done by transpiler, sir?
it doesn't come up under optimization. I mean, the reason it doesn't come under transpilation is because you have seen that um, cutting requires an exponential overhead. So we cannot just put it as a requirement in transpilation, else you will have to end up paying a huge amount of classical or quantum resource for this. So if you want to use this, you have to use that separately as a Qiskit add-on.
Okay, sir. Thank you, sir.
Also, because you don't need that as part of every circuit that you run. It's like
Mm.
if a user wants that for this type of circuit you're running, cutting is deployed, you can use it additionally as part of the workflow.
Okay, sir. Thank you, sir.
One more basic question about circuit depth. How do we calculate circuit depth, or looking at the circuit, or is there any way of calculating? How do we do that?
Yeah, Ritaji, I think you have a way of doing it.
Oh, okay. I mean, no, that's very easy. So what you do is that take a quantum circuit and you find out layers logically. So say again the Hadamard and the C naught, the Bell state example. Since the C naught is also acting on the first qubit, you cannot take Hadamard and C naught within the same layout. So you start taking the disjoint layouts like this. What are the gates that I can immediately apply on the first layer together? If you have a 100 qubit circuit, those also. What are the ones I can apply on second layer? So you kind of combine the gates accordingly like this. Then you just count the number of layers. That's the depth of the circuit.
Okay. So for larger
I thought they was
circuits,
asking
how do we?
programmatically, no?
Yeah,
Yeah, I think they were asking with the command too.
The command
exactly.
is just
Dot
qc
depth.
dot depth.
Dot
qc
depth.
dot depth. I mean, if qc
QC
is your
dot depth.
circuit, then dot depth.
Yeah. Yeah. So I saw you one of the videos running it. Yep. Command. Yep. Thank you.
Professor, like in your example, like qubit one, qubit two, where you apply Hadamard and C naught,
Hmm.
called depth is one.
Depth is 2, because in the first layer you can only apply Hadamard. In the second layer you can apply C naught.
Okay, okay. So it's between qubit one and two. How many circuits are added is
Yeah.
basically depth.
I think one way you can think of it is, uh, okay, I'm sort of composing it on the fly, but it's like, what is the maximum over all qubits? The largest sequence of gates that has to be applied. Uh,
Okay.
I think that's one approximation, but even that is not. Okay, maybe there is one more way. So if you have a, I don't know if you're familiar of this term called DAG, directed acyclic graph. So if you represent the circuit as a DAG, what is the sort of the length of the DAG, or like, depending on how you look at it, depth of the DAG, the largest end-to-end sequence in the DAG. I think that is sort of what will be the depth of the circuit.
Sure, Professor. So with respect to the, I mean, this dynamic circuits you talked about in the lecture, right? So does it alter the depth of the overall circuit? Because it's like it compute and adapts on the fly, right? So what is its impact to the depth of the circuit at the end of everything?
I think it's still there are two parts, right? I think, I mean, maybe you can think of the depth as maximum of those two parts. I mean, or at least I cannot think of how dynamic circuit changes something significantly more than what we know before, because there are only two parts.
Yeah, I mean, adding to what Dinakaran said, usually we will take that as the maximum of the depth. But you are right that if it is a dynamic circuit, it's possible that if you run it 1,000 times, the um, for the feed forward will lead to different parts of the circuit, and the depth of those 1,000 circuits may not be the same. But usually we take it as the maximum.
Right. And I mean, you might also have a case that you have multiple dynamic gates that you apply along the circuit, but Yeah, I mean, the answer can be extended to that. Yeah.
Sure. Is there any papers that have used dynamic circuits extensively and proved any outcomes?
Yes.
Yeah.
I'll just find and give it in chat. Just give
Yeah,
me.
I think very recently also there is some large scale entanglement, right?
Yeah, yeah. I'll have to find those.
Sure. So yeah, that helps, Professor. Mostly on the optimization part, if there are any papers that helps.
Most use of dynamic circuits that we know had been used for some interesting physics demonstrations. I don't know of optimization, but Keep, you know.
No, I am not yet sure about optimization.
But has it solved any problem in physics in real time?
So, okay. No, I mean, if I just want to talk about that, see, one of the let me first share this link. This shows that you can create large scale entanglement using
Mhm.
dynamic circuits, and this long range entanglement would have ideally taken you a lot of depth of the circuit, which grows roughly linearly or at most logarithmically in the number of qubits. Whereas using dynamic circuit, you can bring that down to constant. So this is what it shows. That's already a very interesting use. One of the most useful use of dynamic circuits is error correction, if you think, because when you do the syndrome extraction, depending on what syndrome your system collapses in, you have to make the correction in the system accordingly. So this is one of the major use that we will have of dynamic circuits. Yeah, but Dhinakaran can add
Yeah,
more.
yeah, that's a good point. Yes, correct. I think since you're discussing about applications, I missed that. So that is one of the critical places where dynamic circuits is sort of necessary. I don't know if error correction is already covered, you know, in the lecture. There is a very popular class of codes called stabilizer codes that is on top of which all the modern error correcting codes are built. And typically, like at, I don't know, at periodic intervals, you have these, I don't know, equivalence of detector circuits that you apply that will give some syndromes. And depending on the syndrome, you will apply some, let's say, correction operators to get the qubit back to uh, its original form, or at least that's the intention. And this syndrome extraction, uh, to make that happen, dynamic circuits are essential.
Okay.
Right, but I think maybe the lecture also we covered it. That's one of the critical uses, but we'll also try it for other things. Wherever there is theory that says that if dynamic circuits are enabled, there are many different computational aspects that can be sort of simplified in depth. Uh, I think as dynamic circuits implementation gets better and better, many of these things will come to the fore.
Yeah.
Hello, sir. I have a question.
Yeah, please go ahead.
Yeah, sir, this gate cutting and wire cutting, it will be handled by a compiler completely, or like the user also can do it. And
A user
if
also can do it. So if you look into the three links that I shared, and if you go to the last link from here, let me again share my screen. It'll be easier. So if you
if
come to this,
user can do it, then in what case user needs the wire cutting and gate cutting?
that's up to you to decide. That's up to you to decide. So here is one immediate example where you would need some sort of gate cutting, not necessarily wire cutting. So I don't know if I have the figure here. So yeah, if you look into this figure, you can see that it's kind of linearly going. So q0 to q1, q1 to q2, and suddenly from this last qubit number 108, there is a gate to qubit number 0. So when you want to apply this on the hardware, this would end up requiring a large number of swap gates, because that's a very, very long range kind of interaction. So here is one example where you know that you should be doing cutting. And in fact, if you look into the final results here for this tutorial, you will see that if you just do cutting, how much it improves over uncut. There is no other error mitigation used here. You can see how much improvement it provides over uncut. So that's one immediate example. There are many other use cases that you can see that if you cut, then for say, for example, VQE, if you do that using wire cutting, gate cutting, whatever you want, circuit cutting in general, then you can actually get, you can convert to a much better energy than if you do it uncut and even with say measurement error mitigation. There is one paper that shows this. I can share the paper with you, just I'll find and share it with you. But so that's basically problem dependent, and for now it is up to the user to decide whether using cutting is going to be useful for his or her circuit, and keep in mind the overhead. If it is useful, if you look into these tutorials, it shows you that you can manually put in where you want to cut for the first 3 tutorials. Now, if you say that I have a huge circuit and it becomes impossible to manually look into the position where to cut, that is where this fourth circuit comes in. It's a heuristic tree search kind of algorithm, which is called the automatic cut finder. It automatically finds the cuts for you so that the number of sampling overhead that we say, the number of circuit executions is minimized. You can use any of those.
Sir, okay, it's as you said, it should be handled by user or the decision should be taken by user. But
The decision
based
will
on
be,
what parameters the user will decide? Is it the noise in the circuit is increased and that's why he has to go for
yes, that can be
cutting?
one. I mean, that's how I like to think of it today, because initially circuit cutting was motivated by saying you want to run bigger circuits on smaller systems. That motivation doesn't really hold today. So today, if you see that you want to, you have 156 qubit circuits, but you can hardly what to say, you can hardly run those circuits of size 156 qubits or something. So it should be considered more as an error mitigation technique at this point, and less as trying to run um, say bigger circuits on smaller devices. If you look into this particular work here, again I can share the link if you want. This also shows how you can actually improve upon, you can see that we are actually improving the results by using circuit cutting here. So there are multiple cases where it shows that you can start improving the result using circuit cutting. This is one of the cases. There should be one more. Uh, there should be one more which I can try to find and send it to you. Yeah, let me just try to find and send these links to you.
Thank you.
Excuse me. I have one more question. How do we find out what type of circuit will be a good candidate? How do we find out? Like, there was a question in the assignment also. Is it a QML, GHZ, something like that? So how do we really find out which circuit is a good candidate?
For cutting,
Yes.
okay, so here you need to keep in mind that the more you cut, the exponentially many overhead you need to give for that. So if you have one cut, if you cut a circuit once, if that leads to k circuit executions, if you cut it twice, that will lead to some say 9 to the power k, 16 to the power k, this kind of overhead. So you want to look into the circuit and see how many cuts that circuit would require if you want to split it into two parts. Ideally you want to split it into at least two subcircuits, two or more subcircuits. So to address that question, I would say if you look into a G8Z circuit and try to argue with yourself how many gate cuts or wire cuts I require so that I'll be able to split this circuit into two disjoint parts, versus how many will I require if I have a QML, say a QSVM kind of circuit. In fact, you can get the answer indirectly in one of these two papers I just shared.
Oh, okay.
Anything else?
Sir, I have one question regarding quantum measurement, means control and measurement. So this compilation will be part of control and measurement, or it comes as a separate step?
Compilation happens before, right?
Okay.
It's sort of
Compilation will happen
pre-processing.
before, and then
Yeah.
it goes to measurement and control.
No. Okay. So measurement and control are happening during the circuit execution, right? Compilation is or one of or some of the things that happen during circuit execution. Compilation is one of the key pre-processing of the circuit before it starts.
So basically, there are some companies which will provide the control and measurement hardware, like Zurich Instruments and other other players. So they are nothing to do with the quantum compilation, right? Hello.
Hey, sorry, I think I lost audio for a bit. Sorry, can you say it again?
So there are some players which offers control and measurement solution. Yeah. Those are basically the quartz hardware. So they are nothing to do with quantum compilation thing, right?
Usually not. Yeah, usually not. But I think maybe that warrants going to next level of detail. But usually.
Professor, this dynamic circuits, this measurement and alters the qubit on the fly, right? So is there any um, proven application or it's still in the research phase?
You mean application of
Dynamic.
making things better using dynamic circuits?
Correct.
Yeah, I just shared one paper right on that where
Oh,
long range entanglement can be created using dynamic circuits. And two very important application, as I said, one is definitely error correction. So That's already known that you need dynamic circuits. If you don't have dynamic circuits, you cannot do error correction. That's step one. The other thing also, if you think teleportation requires dynamic circuits, right? Because in some sense, you if you want to build that as a single flow, what it means is that you take the classical information from Alice, whether what is the measurement outcome. Based on that, you decide whether you want to do X operation, Y operation, Z operation. So this is another place where you can think that you need some dynamic circuits. You can still argue that maybe dynamic circuits can be avoided here. I would agree if you argue with that, but in particular, error correction is where this is particularly required. But just look into this long range entanglement creation. That is again another very important requirement.
Okay. Right. So it's not like I can simply replace static with dynamic, but I have to make my.
No. You cannot just replace static with dynamic. I mean,
I see.
yeah, that's not so easy.
So it depends on my scenario, like which where I have to replace my own. Um,
Yeah, I mean, that itself will be a very big research question that if I give you a circuit, a static circuit,
mm.
can you make a dynamic version of it, or can you even prove that a dynamic version does not exist?
Oh, okay. Okay, that's still in research, right? So for static to dynamic, I still have to do a lot of research to
Yeah,
determine
yeah,
if the
yeah.
circuit can be changed to dynamic or not.
Yes, of course.
Thanks, Professor.
I have a question about checking the specs on each of these processors released by IBM. So most of these, I mean, all the specs that I see are number of qubits and all those things, or number of gates that it has, and how their gate layout is there. But what do you mean by a quantum hardware with respect to 50 by 50 circuit? A circuit with 50 with potentially a much larger single qubit depth. So qubit, sorry, and two, sorry, let me read it again. So this is from the assignment. I'm ragging. I don't want the answer, but how do we check these ones? So it was question was there to asking about capabilities of a IBM processor that was released in certain year. So capability is to have a 50 by 50 circuit. What it means 50 by 50 circuit is a circuit with 50 qubits and a 2 qubit slash C naught qubit depth. So what does this exactly mean by this? What
The
are
two
we
cube.
really finding it?
Do you want to understand like what is the 2 qubit depth, or what do you mean by 2 qubit depth of a circuit?
No,
I think
means how,
maybe
what are the
the
specs?
I think first explanation could be what is 50 by 50 mean.
So one thing that is what is 2 qubit depth, if you think. So we just discussed how do you calculate the depth of a circuit by
Depth. Yes.
partitioning it into logical layers. Now,
Uh-huh.
before doing that partitioning, assume that all single qubit gates are gone from the circuit. The reason we do that is because 2 qubit depths gates are often 10 to 100 times more noisy than single qubit gates. So you can
Yes.
always assume that it's almost like single qubit gates are perfect with respect to 2 qubit gates. So logically remove all single qubit gates from the circuit. Now do the same exercise on calculating depth. This is called the 2 qubit depth of a circuit, considering only the 2 qubit gates. Now think of some of the things that you want to have. One very simple thing that you may want to notice is if you want to run a particular depth of a circuit, that particular each of the gates have a particular time, right? So if it is a
Mhm.
2 qubit depth of 50, so that means there are 52 qubit gates, let's say, sitting one after another in layers, not necessarily on the same qubit pairs. But the time requirement of those 2 qubit gates the total time requirement of the circuit will be like sum over the time of 2 qubit gates and the sum over the number of layers. It should not exceed the T1 time of the hardware, because if it exceeds the T1 time, what it says is that the probability that the system gets relaxed and the probability that you get all zero outcome is much greater than half. So, I mean, it kind of gives you just a random outcome irrespective of whatever circuit you have executed. So, one of the way you can think is this, whether this 50 cross 50 circuit is actually leading to a computation time which is greater than or very much comparable to the T1 time.
Oh, okay. Yeah, I understand. But where are we? Where, means, how do you we check these specs
So,
from the?
again, just no, no, just again go to this IBM quantum platform. Let me share.
Okay.
So if you again go to this IBM quantum platform, see it gives you the T1 time here. What is the T1 time? What is the median T1 time?
Oh,
If you
okay.
want to know what is the time of a 2 qubit gate, this is the gate length. So that gives you a median gate length is 68 nanoseconds. So now
Okay.
whatever device you want to look into, this is kind of one of the latest device that we have. So this will be super good, all of these. So if you, sorry, now you can say that okay, 68 is the um, length of each 2 qubit gate. Say there are this many layers, there are 100 layers, then there are 6800 is the total length that I require for that. That you can follow up with measurement, and if you want to find out the length of measurement, that also you can do from here, this readout length. So it's 2200 nanoseconds. So you can find what is the total length of the circuit in terms of execution time. When I say length, it's like in nanosecond. What is the total duration of the circuit? What is the allowed T1 time? Are you exceeding or getting very close to the T1 time?
Uh, sorry. Are you asking me?
No, no, I mean, that's how you can answer the question basically.
Oh, okay.
Professor, what do you mean by transpiling multiple times the same circuit?
So, I mean, what it means is, see, transpilation is basically a heuristic process. I mean, as I was telling you, it's an NP hard problem. So, whatever is done today is heuristic, and there are some stochastic steps which are taken. So, whenever you have such stochastic steps, it's always a good practice to transpile the circuit multiple times, because that can lead to different depths depending on how the stochastic steps go in between. So if you just transpile the same circuit say 100 times, in general, not for all circuits, you will see that the depths differ slightly. So just keep track of the circuit with the lowest depth, use that one.
Oh, okay. So it is possible to have different transparent
Yeah,
circuits.
yeah, yeah, it's always possible, because I mean it's a stochastic method. So
Oh, I see. Okay, thanks.
Yeah, it's probably an exercise for you to look into the different steps and then see which ones are deterministic, which ones are randomized.
Sure.
Are there TAs for this also? Anubhav? Anubhav is a TA?
And this I am not aware of. I'm
Yeah,
not.
last time also I asked about this question. So, who are the TAs for this? Because do you going through, I am getting some doubts, and usually earlier what we used to do is we used to post them in a Discord channel, and they used to help us.
Hmm.
But this time actually is we are trying to get some answers. So for these modules, whether Anubhav will be doing or who will be helping, 7 and 8 especially.
We can check and ask them to respond.
Sorry, can
Yeah,
you?
I mean, it's better if you ask the NPTEL code support team for that.
Yeah, I asked them, but nobody's answering. So I'm not sure whether you know anything about it.
No,
Maybe
no,
I'll
no.
also ask Professor Prabha to uh, like look at that and then get back to you guys.
Okay, thank you.
Yeah, okay. There is a question. I think these are really great questions. Like, what is the optimal orchestration strategy between classical and quantum compute in hybrid algorithms? I don't think we have an answer to that. That's still an open research question.
And maybe for this part, we are not really looking at the most optimal one.
Hmm.
I mean, we just keep iterating and building better and better things. And also, we are still exploring what are the most useful quantum algorithms to use. So, you know, whatever is optimal now might differ when we have new quantum algorithms come up. So, for example, we had VQE as interesting algorithm to run. Now there is thing called SQD, and hence the workflow orchestration thing differs, right? So yeah, it's an evolving area of research problem. Maybe let's see if we can share the QCSE architecture one that and maybe also the working group paper, just as two references to survey papers, right?
Yeah, yeah. Okay, this survey paper I can immediately find. Yeah, this is one paper that is very recent, which talks about reference architecture in a quantum centric supercomputer. The idea is that you have a scenario where quantum, classical, and GPU, HPC, all of them are sitting together, and what would be a good reference architecture for that? Uh, how does error propagate when we reconstruct? So you were saying anything, Dina?
No, no, no. I was just asking the reference for the working group, QCSE material science working group. But anyway, I think that's anyway.
Okay, how does error propagate when we reconstruct results from subcircuits? So reconstruction is itself noise free because that's classical. But again, if you ask how does error propagate, I would say this is still a question that is unanswered. Um, so what we know empirically, not analytically, is that the overall error of your reconstructed result is dominated by the maximum error of your subcircuits. Whichever subcircuit has the maximum error, that is the one which dominates the imperfection of your reconstructed results. This is something we know numerically, empirically from running circuits and everything, not from some analytic calculations. So, yeah, uh, how does error propagate? This is again something I think quite unanswered at this point. And if you want to take it up, I mean, that's a really good research question to answer. And there are still how do dynamic circuits impact latency and coherence time constraints? Hmm. Okay. So dynamic circuits today, yeah, I mean, if I even want to talk about a year back, when you are doing dynamic circuits, you need something like, when you are making a classical decision, so based on the output of your mid circuit measurement, you are making a classical decision whether to do this or to do that. And usually this classical decision making is comparatively slower, I mean significantly slower than the quantum gates and everything. Therefore, there was a lot of trouble even maybe a year before, where while you are making this classical decision, the coherence of the system gets destroyed. But now if you install the dynamic circuits, and if you now want to do dynamic circuits, not install, basically that's installed in Qiskit, but if you want to do dynamic circuits now, there is a gen turbo or some version that has been created from the product team, and it is a super fast way of making these decisions. Therefore, there is not a great loss of coherence time when we are using dynamic circuits. uh, I am not sure I follow this question. How do dynamic circuits affect parallelism in quantum execution? Can you elaborate on this question a bit? What do you mean by parallelism here?
Yeah. For the parallelism is like we are parallelly executing two circuits, parallelly happening circuit execution. Parallelism is
Oh,
sorry.
so you mean there are multiple gates which you can operate
I
parallelly?
mean multiple gates that are operating parallelly.
Yes, yes, of course. So that is definitely in some way affected, because when you are saying that you need to look into the outcome of a mid circuit measurement and make a decision what that next gate will be, you cannot previously like assign everything that this gate goes here, that gate goes here. So that's again a big challenge on transpilation, that on that go you need to decide that, say, okay, when I measure, if 0 comes, then I apply circuit 1, if 1 comes, then I apply circuit 2. Now you cannot have this circuit 1 and circuit 2 parallelly transpiled beforehand, because this can keep changing. You can have multiple of these mid circuit measurements, so it's not necessarily a one time go. On that point, once you have seen the outcome, you need to make that decision on how to place the following gates and how to run them parallelly. So of course this is a again a big classical challenge, but I think the transpiler does it pretty well at this point.
Any official documentation or books I can read about these things? These are architecture level things that what happens at the very circuit level.
Books, I am sure there are none. I'm not sure if there are official documents. Dina, do you know if there are official documents
Around transpiler, or
around how
like,
dynamic circuits, I mean, when dynamic
I
circuits
think,
are there, how transpilation works and everything?
oh, I think the dynamic circuits tutorial and uh, let's say documentation, maybe that's the best one we have at this.
No, basically on parallelism. The point is about parallelism.
No, parallelism and dynamic circuits don't go hand in hand, right? As we mentioned, those are two
No, I mean,
different.
one point that comes into play is, of course, true that when you have dynamic circuits, you cannot just pre-transpile all the gates, because you need to make a decision at that point which gates will be placed on the hardware. I still think that so you need to make a decision at that point, but you can still use the parallelism of a transpiler at that time. So say a 0 happens, and you know that you have this set of n gates now that you want to put on the hardware. You can still ask the transpiler to do it for you. Usually the transpiler will do it for you very efficiently at that point.
Okay. Okay. Yeah.
The question that you can ask, which at least till a few months back I knew was not very well answered, is that parallelism is not the main problem here. The main problem is that, say, when you do a mid circuit measurement, then if the outcome is 0, you have circuit 1. If the outcome is 1, you have circuit 2. these two circuits can require very different layouts. These two circuits can have very different interactions. If that is the case, how do you like manipulate the saber algorithm to find a very good layout? That is a very big question, I think, which is still largely unanswered.
Okay. Okay. Means you have to, how do we manipulate stable algorithm based on the outcomes of the two circuits who are very
Yeah,
different of each other?
yeah.
My
How, because
understanding is
because
that,
the
no?
layout you have to decide beforehand, where on which qubits you want to place, and do you want to place it based on the easier circuit, or do you want to place it based on the harder circuit? How do you really do that?
Okay. Okay. And one more question is there that for the I pasted in chat.
So this is the we get a fixed instruction set architecture,
In
but in
classical
quantum
compiler.
computing, it does, but it doesn't also. So all the instruction set architectures that you will see on a quantum computer today is what is called the Clifford plus T library,
Mm-hmm.
and Clifford plus T is universal. So Clifford gates will consist of all single qubit Clifford gate where compilation is easy,
Mm-hmm.
and there will be 2 qubit Clifford gates as well, which can be C0, CZ, or whatever. Um, right now, I think CZ and C0, these are the most, or there are some architectures which use ISWAP or something like that.
Okay.
But T gates are also single qubit gates. So eventually it breaks down into the minimum number of single and 2 qubit gates that you want for your case. In IBM system, you see that the 2 qubit gate is CZ today. The single qubit gates are X, SX, and the T gate is basically RZ. It's also a single qubit gate. But eventually, if you read the papers on general compilation, they will often say that we are doing this for Clifford plus T library because that's universal.
Okay. Okay. And the immediate representation that happens in classical computers, how does it differ in quantum computers?
What is the immediate representation? What does it mean? I mean, what sort of representation here?
Means means in classical computer we convert it to machine level code and assembly level code.
Oh, so it
So
immediately gets converted into what is called a QASM, quantum assembly language. So just like
okay, there is
classical.
assembly language for this.
Yeah. So from Qiskit it goes to chasm. From chasm it will go to say pulses in particular. Those each of the gates will correspond to a particular pulse. And since you are saying that say I want to apply Hadamard on qubit one, that means it tells that at this point there is a Hadamard pulse which needs to get applied on qubit one. So whichever coupler is acting on qubit one, it will send the control there that you need to apply this Hadamard pulse on qubit one. Like this, it will go.
Okay, so where can we learn about this quasm? Means like assembly language we have learned in BTech now. So where can we learn
Yeah,
about
yeah.
this quasm
Chasm,
method?
you can just search. I am not immediately sure where, if there is a paper or not. I mean, you can even look into the documentation in IBM. I am sharing that link with you here
Okay.
in chat. It's called Open Chasm here.
Mhm.
Yeah, here you can get a lot of details on how Chasm works and everything.
So any level of circuit, dynamic circuit or just static circuit, it converts into chasm only at the end.
Yeah, 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 yeah.
Then it
Chasm, you
will.
can. Okay, I see there is also a referred journal paper in this link that I shared. Yeah, in any type of circuits, because eventually, even if it's a dynamic circuit, see, it's just a measurement, right? It's a measurement followed by some gates, which are again coming from Clifford plus T library. So it will still have an open chasm kind of representation.
So at the end it goes to the chasm and then it goes to the machine coding.
Yeah.
As per the classic understanding only. Okay.
Yes.
Okay. One immediate level thing was chasm only. So similar to chasm. Mm, okay. Okay. Thanks for the answering my question. If anything comes, I will ask.
Yeah.
Thanks.
Sure.
Here before IR, I was saying that IR is like before compiler we go to before assembly is created. There's some representation is created, like some abstract tree, syntax tree is created in compilation or something like that. So in quantum, what is the equivalent of that? Means when a high level code, how young Java code is done, like function main function is there, printing out
Mhm.
something, it converts into some immediate representation in compilation, but before assembly. Before assembly is generated, the representation is created like AST or something equivalent. I'm not remembering properly, but yeah. So what is the equivalent of that happens in quantum? That I was asking properly in that question.
I'm not sure if there is an even intermediate step between going from Qiskit and Chasm.
I think the DAC circuit is one
Yeah,
intermediate
DAC
step.
circuit. Okay, yeah,
Right.
maybe.
And I think that is also going to evolve when we move towards fault tolerant computers. So, yeah, as of today, yes, DAC circuit is one good intermediate between these.
That circuit means spelling of that is
DAG, so it's a directed acyclic graph. So yeah, I think the representation maybe what you are looking for is from circuit it is converted into a graph. It's a directed acyclic graph. um, that's the representation. Everything that Qiskit does, usually it does on the DAC circuit, not everything, but most of the thing that Qiskit will do to evolve the circuit, update the circuit, will be done on that DAC circuit, and then it goes to the chasm form.
okay. So in intermediate representation is the graph only, similar to the compilation
Yeah,
part.
yeah, yeah.
There we built a tree. Here we do a graph. So it is an undirected graph or directed graph. Means how
No,
is the
it's a
graph
directed acyclic graph. That's DAG.
directed with weights or without weights?
Without weights.
Without weights. Okay. Okay. So to traverse that graph, we use detectors or what is used? Where can we read about that graph?
You can read about that graph and everything just here. I mean,
Can
again,
you
let
just
me.
guess the name of the graph? Yes. How
Yeah.
it is traversed and how is this? Okay. Okay.
So if
That,
you just look into here, you can take any circuit you want and you can just convert it into a DAG and you can see how it works. In general, the idea is that when a circuit gets converted into DAG, then in particular, the nodes are the starting nodes are the qubits. And say you are, say take the example of that Bell state, right? You have a Hadamard followed by C naught. So you will start with two vertices which correspond to the qubits q0 and q1. From q0 you will have a directed arrow to another vertex which is a what's called, which is a gate, which is the Hadamard gate.
okay.
Then after, then from Hadamard gate you will have an arrow, and from q1 you will have an arrow which goes to the C0 gate. So it creates a dependency that the first gate on q1 is C0, but you can apply C0 only after q0 has gone through Hadamard. So it also creates that dependency kind of nature.
Okay. Okay. So in dynamic cycle, how does it happen? These are example of classical.
There's the same thing, the same thing. The dynamic circuit is will be the same thing in between. So if it is a normal circuit, then the final nodes are the measurement. If it is a dynamic circuit, then from measurement you can even have two nodes going out maybe.
So the graph evolves dynamically also.
Yeah, exactly. The graph will evolve dynamically. So you
So
can
there
have
is
an
a
intermediate node which is a measurement.
so what is the time complexity and space complexity taken if the depth of the circuit is very large? For example, 1,000 qubits or 1,000 qubits can be a maximum for now. But what is the time complexity of that graph? Because it's getting deleted, updated at a very instantaneously, no?
Usually DAC circuit will not get deleted updated, right? Because DAC circuit is, once you have the circuit, you have a DAC corresponding to that. So you can delete or update stuffs in DAC circuit. Coming to your question on space complexity first,
Hmm.
the number of nodes in that circuit will be the number of gates plus the number of qubits plus the number of measurements. Number of measurements is usually the number of qubits. So it's basically proportional to the number of gates and the number of qubits. That
Number
is the, yeah,
of
that is the number of nodes there. If you
all
want,
all the
yeah,
components in the quantum circuit are the nodes of the tag.
yeah, yeah.
Okay, and
If you want to change something within DAG, it's basically a graph traversal, right? You have to start from the beginning and you have to traverse through the graph and find the node that you want. So it's a general graph traversal. You want to go and find the node that you want, and then whatever you want to do, say you want to say that on the node it was a Hadamard gate, I want to change it to say a Z gate. So you need to traverse and find that node and then make an update to that node. So that graph traversal time it will take, I mean, depends on how you do the traversal, maybe n log n or something. I'm not very sure about this. What will be the time complexity? But it will depend on how you do that search. Whether
so it
you do a,
takes the classical time. You're saying it takes the classical time only that happens, not
yeah,
something.
yeah, because it's a DAC circuit is a classical representation. This has nothing to do with the actual quantum implementation of this. So this will just be a classical overhead.
Okay, before converting to the quasar.
Hmm, hmm.
Okay, after quasar, it becomes something with classical, with our quantum perspective.
Yeah, it becomes a pulse, which is basically then applied to the hardware.
So pulse is like a wave.
Pulse is a wave. Yeah, exactly.
So there can be constructive interference and destructive interference, and
There
every
will be, I mean, there will be constructive and destructive interference, and that is how basically any quantum algorithms work. The way you want any quantum algorithm to work is that the different candidate solutions will interfere with each other. The final good solution will interfere constructively, the other bad candidates will interfere destructively. So that's how you want a quantum circuit to work, or a quantum algorithm to work rather.
okay, okay, no issues. Thanks. So just the tag and simple. Either we use DFS, DFS, or something like
Yeah,
Digista and
exactly.
then okay, okay, okay. I will read about it. Thanks. Are there any optimizations happens on the graph? Any external optimization algorithms used to optimize the graph?
What do you mean by optimizing the graph?
Means optimizing is like if you take from one node, it takes reducing the time complexity and space complexity is the optimization. No? Like BFS, DFS is not applicable everywhere in the graph problem, but sometimes data comes, sometimes Floyd Balshall comes. Different algorithms
No,
are
no.
there, no, for
See,
the
see. So see. The first and foremost thing that we need to understand is that you are giving it a static circuit. So I am not trying to find a property of that graph in general. If you want to find the property of that graph, then you apply some algorithm, some graph algorithm, be it BFS, DFS, or whatever, something else that you want. But from a circuit, you are creating a graph, and the transpilation steps, many of these transpilation steps actually work on that DAG circuit, that graph representation of that. So those are algorithms which try to evolve. So that's a transpilation step. If you want to evolve that graph for some reason, like the transpilation tries to find a more optimal, say if you have used say two Hadamards next to each other, then the transpiler will kind of combine them two and make it identity remove the gate. So these type of optimizations the transpiler does on top of that graph. But That's like problem dependent or context dependent.
So in dynamic circuits is like we are measuring at the middle of the
Hmm.
circuit, na?
Hmm.
So dynamic circuits, the graphs are also dynamic, na? Because the measurement is in the middle. Something can
Yeah,
happen. So
yeah.
in that case, the optimization is we needed, na?
Yes. So no. So what sort of optimization? Once more, when you measure, you get an outcome. The corresponding circuit that you are getting, that circuit, there can be mainly two kind of things in terms of transpilation. What you want to do there are mainly two kind of things. You want to find out whether there is a better representation of, again, let's take that example that you are measuring. If it is 0, you apply circuit 1. If it is 1, you apply circuit 2. Now you may want to have a more compact representation of circuit 1. I have used 10 gates for circuit 1. Can you do that using 5 gates or 6 gates, 7 gates, whatever? Same for circuit 2. You can ask this question. This question, these two chunks of circuits are static. You can do this separately even in the beginning. This has nothing to do with mid circuit measurement. You can say that, okay, whenever I need C1, I will put C1. When I need C2, I'll put C2. But in the beginning, I can take a more compact representation if I can represent each of them with lesser gates. This I can do just before I even start that circuit execution. What I can't do in the beginning, that I was telling, is that how to select the layout. That's a big question, because C1 and C2 can have a very different optimal layout, and that I cannot select from beforehand which of these layouts will have to be there. So right now, the Saber algorithm will statically calculate a layout for that circuit, and that may not be the best when you have such a dynamic scenario. But if you are thinking of optimizing the circuits in terms of the number of gates, then that can be just done before the circuit execution starts. Consider both of the cases and just optimize them. So
Okay.
that doesn't require dynamicity or anything there.
Okay. 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 Yeah. Got clarified on optimum. Yeah. Okay. Thanks. There are no research papers on this point. Any means if I want to learn about just how the quantum circuits work and mean the chips that are being created by IBM and Microsoft or Google, and how do we know about what is going internal and what are the whole architecture of that? So how do we learn about that? Are there any books or architect papers
You
that I
can
can?
look into how normal superconducting qubits work.
Okay.
More information on precisely how IBM quantum device works, that you will not get.
Okay. I will not get.
No, that you will not get. That is, yeah, that is always a trade secret.
Okay. Okay. That is proprietary. I got it. Yeah. Okay.
Here
Thanks.
is one thing that I can share with you. If you find these things, you or anyone else, if you find this interesting, there is this open source software called Qiskit Metal. Now it's called Quantum Metal. You can use this to actually emulate creation of a chip. Here you can even say what sort of pulses will go, what will be the waveform of that pulse, what will be the connectivity between the qubits, and you can test how your design works. This is an emulator that you can use.
Okay. This is later. Okay. Okay. This is emulator. It doesn't need any GPU or CPU. Right? It will work on CPU, no? It will not any needing any
No, no,
GPU.
no. It will work on CPU.
Okay. Okay. Okay, thanks.
Anything else? Okay, if not, I think we can end. And if there were actually questions that Dina also wrote in chat, if there are questions that you would have really wanted to ask Dina Karan, then just feel free to email him.
One last question. Are there anything like distributed systems in quantum? Like in
Yes,
classical, we have distributed systems. Are
yes,
there anything like that?
yes. I mean, you can just search this term distributed quantum computing, you will get a tons of papers and everything.
So it is means real world applications are there on that or not? Like we have distributed computing very much in classical. Everyone is using that. So are there any things like applications of distributed computing?
not
Quantum.
in not in that way. So see, there are many. So see, quantum is there for just 10 years, right? It's exactly 10 years that we have a quantum computer. So if you want that, if there are already protocols that are being shown and demonstrated and working right now, no, we need to give that a bit more time. But are there theoretical stuffs? There are. I mean, that's why I said just go and search this term distributed quantum computing. You will get a ton of theoretical stuffs. And of course, there are efforts ongoing to implement those. IBM, in particular, tied up with Cisco recently. You can even get that announcement online if you want to build distributed quantum computers. So, there will come applications of those in reality.
Okay. 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 Distributed quantum computing. Okay. I will read about it. Thanks.
Hmm.
Okay.
Okay, if nothing else, I think we can end here. Thanks for all these questions and everything. And yeah, feel free to reach out if you have more questions or queries, email or LinkedIn, wherever you want. Okay, then bye, everyone.